Our guiding principle so far that's motivated the introduction of classes has been that there are times when we want to define a type that has complete control over every aspect of the lifespan of all of the objects of that type. So what I have here is an imaginary class called matrix. This is sort of a mock-up, so we're not actually going to write anything useful here. We're just going to talk about this concept. I have this class called matrix where I might want to represent the concept of a linear algebraic matrix. For example, we could decide to define a constructor that takes two arguments, and the idea here is this value that I'm defining on line 17, the variable a, sort of corresponds to a 3x4 matrix, the kind of thing you'd see in linear algebra. So there's 1, 2, 3, 4, 5, 6, 7, and so on. You get the general idea. This might be an easy abstraction for the idea of a linear algebraic matrix. Similarly, on line 19, I'm using a matrix, but in this case, it is a matrix with 3 rows and 1 column. That might be a way of representing a column vector. So I could represent, as you recall from linear algebra, I could represent a vector as a certain type of matrix, usually represented as a column, because all of the usual operations you do on vectors sort of work pretty well if you represent a vector as a column. Okay, so I could do that. I could implement a class for that, but on the other hand, I could do the same thing in C. I could use an array in C to represent a matrix, as you likely did in CSC 111. So what am I getting at here? Well, we know already that I could make a class called matrix that defines constructors and destructors and thereby gains complete control over who can create the object, when they can create it, and things like what happens when it gets destroyed. I can use the features available for encapsulation and access control to decide how the elements of the matrix are viewed from the outside, who can modify them, and when. And so far, that has been our running theme, that we have all of these technical things we can do inside the class to protect its contents, to make sure the class is encapsulated. And then we, I guess, define functions to present the abstraction that we want. So the abstraction is this is a matrix. And I guess the point I want to make going into this is much of what we did last week was focused on the encapsulation aspect. How do we hide the internals from the outside world? It wasn't so much focused on how to create a convincing abstraction. We did implement abstractions by defining functions. The case I want to make going into this week is there are a few other features we can leverage to present a wonderful abstraction, to present a perfect, airtight abstraction to the outside world. So suppose that I have matrices. I've got a matrix A, I've got a matrix B, and I've got a vector C. Suppose I'm working in linear algebraic context. So I'm not talking about C++, I'm talking about linear algebra. What kinds of things might I do with matrices? Well, let's see. I might add the matrices together, and in math, I would write that like this, A plus B. I might multiply two matrices. So in math, I would write that just as AB, because of course we don't bother writing in the operator for multiplication. I might want to ask questions like, can you find me a vector x such that AX equals C? And if we stare at these things, we do notice, hey, this looks a bit C++-ish, the plus operator. We should know that this probably isn't a C++ expression no matter what I do, because it looks a lot like it could just be a variable called AB. And this relationship isn't something I would typically write in C++, but it's an operation I might actually want to perform. What I want to introduce today is a concept that allows us, if we want to perform operations like adding matrices, multiplying matrices, or solving systems of equations, we have a lot of options in terms of notation for that. So obviously it's true that if I want to add two matrices together, I guess I could write a function like matrix add matrices. And then it takes a matrix A and it takes a matrix B. I could just write a function that takes two matrices and adds them together. You might have done exactly this in CSC 111. This would be fine. I could do this. I could make this a member function of the matrix type. But my claim is to present the abstraction of a matrix, I want the matrix to look as authentic as possible. I want it to look as close to the way I would use a matrix in mathematics as I possibly can. And I know that the plus operator exists in C++, so why can't I define a plus operator for my matrix? And it turns out that I can. This is a video introducing the concept of operator overloading, defining my own meanings for operators. And in this video, we are not going to talk about the matrix type, although the idea of defining your own operators for matrices is a classic example of an application of operator overloading. The reason we're not going to talk about it, despite the fact that it's a great example, and that, as if you know me, you definitely already know, I love linear algebra. It turns out that that's a lab exercise that you're going to do in a different setting. I don't want to spoil it for you. It wouldn't be nice to the poor lab instructors if I take away that wonderful example from them. So instead, I'm just going to present it as a mock-up, and it's something you're going to end up writing yourself later. I will go into great detail about a different classic application of operator overloading about 2 or 3 videos from now. In the meantime, I want to introduce the general concept of making up your own operators for your own types, or maybe for types that already exist. So what I have in this file is just a mock-up. So I've got this imaginary type called matrix. We can agree that maybe there's a constructor that tells us how big to make the matrices, how many rows, how many columns. And what I want to do is I want to be able to use my matrices in a very natural way. And that is right up to and including maybe using C-style initialization. If I declare a new matrix, I of course could set it to be a copy of the result of this apparent addition operation with a uniform initializer. But I think we should go all out. If I want to present an abstraction of a matrix, a perfect abstraction, maybe I'll even just sort of give in and use C-style initialization because it looks a lot more like math. Okay, so what I want to do is I want to define the operation A plus B to be able to add 2 matrices together. And it turns out, and maybe this doesn't surprise you, but if you define your own class, you can't just use a plus operator on it. It doesn't work that way. You have to give that a meaning. I also want to define A times B to be matrix multiplication. And although you might agree that if I have 2 matrices, adding them element by element, I guess is a sort of obvious thing to do, it's hopefully clear to you that the compiler wouldn't automatically know how to multiply matrices. You have to tell it. So the behavior of an operator is something non-trivial that you might have to specify. I might also want to compute the negation of A. So not just, I don't want to subtract A from something, although I could define that. Instead, I want to be able to take every element of A and negate it. So you could think of this as sort of multiplying it by the scalar -1. All 3 of these lines show off operators. So in C++, for the most part, there are a lot of operators. Almost all of them support what's called overloading. And you might recall the term overloading from a few weeks ago when we talked about function overloading, defining multiple functions with the same name. Operator overloading is defining new meanings for existing operators. One thing you can't do in C++ is invent your own operators. You can reuse existing operators in odd ways, but you can't make up new ones because that would require the compiler to do a whole bunch of gymnastics that it's not capable of doing, involving things like, if you make up your own operator, what is the precedence? Questions we don't want to have to worry about. But if an operator already exists, you are allowed to define a new meaning for it. For example, what happens if you apply that operator to types that you've created yourselves? And that can be a binary operator, like the plus operator, or it can be a unary operator, like the negation operator, or the logical not operator. It can also be operators that we associate with arithmetic, like these 3, or it could be operators that we associate with comparisons, or other logical operations. So the equals operator to ask if 2 matrices are equal. Well, if I'm working with a lot of matrices, I probably want to do that. I want to be able to easily ask, are these 2 things equal? The same way that I can add 2 strings together. And adding strings does have a well-defined meaning that we're used to by now. And I can ask if 2 strings are equal using the equals operator. That, in fact, is a result of operator overloading. It's also an example of how the language is holding nothing back. So when you use strings, you can use the plus operator on these strings, these smart objects that aren't just ints or floats, but yet they have a plus operator, and they have an equals operator. And there are languages where you can use plus on strings, and you can ask if strings are equal. Java is an example of a language that defines a plus operator on strings. And there are languages that do that, but don't allow you the same facility. So in Java, you can add 2 strings together. Even though strings are objects, they're not just ints or floats, they are objects. In Java, you can add 2 strings, but you can't define your own plus operators for your types. The reason is, strangely, that the Java designers apparently had an ideological opposition to operator overloading. They said it's a bad idea. They said it's terrible, you should never need it, you should just write functions instead, although in Java they don't call them functions. It's strange, though, because the language designers turned around and decided to give you a plus operator on strings. That is to say, they broke their own rules because they figured, hey, you have to follow these rules, but, we're the designers of the language, we don't. I don't like that. I think if a feature is useful, it should be for everybody. If it's not useful, then nobody should need to use it. That's one of the reasons I like C++ and the fact that it holds nothing back. Any clever thing the language designers can do, you can do too. So here's an example of 3 operators I might define for matrices if I were writing a matrix type. And I would say any matrix object in C++ probably actually has these. It's a very common abstraction to use. It's pretty likely I'll want comparison operators too, because if I'm working with these objects, I might want to ask if they're equal. But I'm welcome to define any meaning I want for an operator. So if I decide that I want to solve the system AX equals C, I want a vector X that is a solution to AX equals C, I am welcome to commandeer some operator and decide that it's going to be used for that purpose. So I could decide, for example, that writing A modulo C, where A and C are both matrices, is the operator I use to solve a system of equations, if I don't just want to use functions for that. That's valid. You can define any meaning you want for an operator. The compiler's not going to judge. Although, of course, if your goal is implementing a good abstraction, you should define meanings that make sense, just like how this is matrix addition, exactly what we expect. And when I add 2 strings together with the plus operator, that means something logical as well. And the idea is operator overloading. So, of course, the first question is, how do I do that? Before I worry about matrix types, how do I define my own operators? And there are a few ways to do it. I'm going to start in this video with a pretty basic one. Before I do that, though, let's set the stage for an application we can actually hack away at today. So what I have here are 3 different functions that work with strings that are sort of the function version, the C-style way, although I'm using C++ types, the C-style way I would implement special operations like adding strings together. So here's a function string plus string, and it goes out of the way to avoid using the plus operator on strings, although that does exist and I can do that. So what I do is I take 2 strings, I make a result string, and then I just go through my first string, S1, and I add every character to the result string. I then go through my second string, S2, and I add every character to the result string with pushback. So I just concatenate 2 strings manually with this string plus string function. What if I want to add an int to a string? Well, I suppose from the context, if I have a string like the word hello, and I want to add the number 6 to it, I think it's reasonable that we could interpret that as I want to take the string and then mash it together with a string version of that number. So it'll be hello 6. So if I give you a string and an int, and I say add the int to the string, what I'm really asking for here is a new string containing the original string s1 plus a string version of the int I. Okay, so here's how we could do that. First, we could convert I to a string. There's this function std_toString that converts some numerical value, like an int, to a string. I convert that to a string, and then I just add the 2 strings together as before. And you can stare at this and realize, hey, I could just call string plus string here to add the 2 strings together. But whatever, I'm not doing that. And then how do I add a string to a float? Well, I take my string and I take my float. I convert the float to a string using std_toString, and then I add the 2 strings together as before. A note for later, in C++20, there is a more powerful way of converting floats to strings called Std Format. And I was excited to adapt this example from the old C++17 option of toString, which isn't very flexible, to use Std Format, which is available in C++20, which we are using. I discovered, though, that although G++ tells me that I can choose C++20, G++ doesn't support this for some reason. And a weird sort of fact of life with C++ compilers is when a new standard comes out, it actually takes a couple of years for compilers to actually fully implement it. And G++, as of January 6th of 2022, does not support fully support C++20. Although I should add, there are newer versions of G++ than the one I'm using. I'm using the one that came with my operating system, which came out around mid-2020, I guess. And so I suppose by now there is some version of G++ in the pipeline that does support Std Format, although the ones you're likely to find in modern operating systems tend not to at the moment, which is too bad. The default C++ compiler that comes with Apple stuff, so it's called Clang. It also does not fully support C++20 yet. Maybe by the time you actually watch this video, the compiler does. But anyway, whatever. In the meantime, we'll continue using std_toString. So I have functions here that add strings together, add a string to an int, and a string to a float. And we'll just demonstrate that they work. The reason I'm doing this is to show that what I'm actually performing, the operation I'm performing here, is something we can deduce from first principles if somebody hands us this magic function std_toString that converts numbers to strings. Okay, so I can do that. The question is, if I want to add strings, I don't want to write string plus int. I'd like the nice notation of being able to literally write my string A plus the int x. I want the same convenience that I get when I'm adding two strings together, as we've been doing all semester. And I get to have that. So here is the actual code I want to work on. So here I've got a string s and a float value called v, which is 10.6. And of course, if I would like to concatenate s with the string representation of v, I could write what I have on line 20. I could actually use the string plus operator. I could just use it to add the result of converting v to a string to the original string s. I guess that wasn't the code I wanted to compile. So I want to define a plus operator that does this for me. I want to be able to actually write what's written on line 23, s plus v. Okay, so we'll just show off that the template runs as written. So I can still use std2string to actually turn v into a string and then add it to s. What I can't do is this. So if I write, actually, that's a dumb way of doing this. Okay, so if I write s plus v, I'll just uncomment so we have both versions. There we go. If I write s plus v, the compiler has some trouble. And we might have seen this by now, but there are times when the compiler really seems to have a lot of trouble, and this is one of them. What the compiler is actually doing here, and you might have seen this a lot when you try and print stuff out, and we're going to see it again a few times this week. The compiler is clearly having a very, very bad day. But if we scroll to the very beginning, it says error. There isn't a match for operator plus. As if it's implying maybe there could be a match for operator plus. It says, well, I've got a string here, aka some hideous name we don't want to think about, and I've got a float here, and I don't know how to add them together. And then the rest of what it says is it throwing a tantrum because it wants to prove to me that it wasn't its fault. The poor compiler thinks that I'm going to blame it for this. And so what it's telling me here is all the different operator pluses that it tried and how none of them are going to work. For this example, this stream of errors is sort of hard to read. We'll actually try parsing it in a couple of videos. We'll try and see if we can reverse engineer what it's really trying to tell us. Ultimately, though, what it's saying is I don't know how to add string and float. But fortunately, in C++, I'm allowed to tell the compiler how to do that. So we notice that it is natural to try and write string plus float as a function. So I could do something like this. And in fact, actually, why don't we just borrow this function and just bring it in? So this is a function that takes two arguments, a string and a float, and returns a string. What I want when I write s plus v is that function to run, but I want the convenience of writing it as an infix operator, as s plus v, not as a function call. But we can think of the plus operator sort of as a type of function that takes two operands and returns a result of some type. And the language does as well. If I want to make my own operator that has certain behavior, I write a function that does the same thing. So for the plus operator that adds two things, it takes two arguments, which can be of whatever types I want, and returns some value. If I can write a function of that form, I can make it into an operator. And all I do is, instead of a function name, I write this, operator plus. This is telling the compiler that every time it needs a plus operator that takes a string as the left operand and a float as the right operand, it can use this. The same rules apply to this as apply to functions. I'm only allowed to define one plus operator that takes string on the left, float on the right. Just like how I would only be allowed to define one function called string plus float that takes a string followed by a float. I could define multiple functions called string plus float as long as their types of the parameters were different. But I'm not allowed to define more than one function with the same name and same parameter types. And the same is true of operators. But there is not already an operator that adds a string to a float. We know that because the compiler certainly made no secret of that with its stream of errors. Therefore, I can define my own. And I'm going to try doing that. And there's no error, and now I run it. And there it is, value equals 10.6. I have now designed my very own plus operator to fill in the missing case of string plus float. And there is a long list of operators that you are allowed to overload to define your own meanings for. The only real rule is you can't define an operator twice. So if, for example, there already is an operator to add string plus string, so I can't define my own operator for that. But I can define an operator for string plus float. Now, a note, some of you watching this know a little bit of C++ operator overloading already. It is true that it's considered a little bit sloppy. It's considered to be sort of bad style to gratuitously define operators operators on types that you didn't create yourself. So me making up an operator on string and float, given that I did not define the string type and I did not invent the float type, me making up my own operator can be considered a little bit tacky. It's sort of weird to do that, but it's valid. You are allowed to do it. Generally, we'll see we define our own operators for types that we've created. So string plus a type I've created, or a type I've created plus string. That would be a very valid, healthy use of an operator. It is valid to do this, but sometimes it's a bit tacky to define operators that operate on types that you aren't really responsible for. It's sort of getting into somebody else's business. I should also add that really this is a little bit unnecessary. If I want to add a string to a float, I could just try, delegating that to the string plus operator. I could say return s1 plus std of toString of the float. Because I know this returns a string, which means this operation is going to be string plus string. So it's not the same as string plus float. So I could just basically defer this whole thing to the strings plus operator. We can see that that works as well. So in C++, I have the ability to define my own operators. If you want to know all of the operators you can define, I'll post a link alongside this in the notes, because there's this huge list of operators we can redefine. We're going to go through quite a few of them this week, but there are a lot more of them. And basically every category of operators that you find yourself using commonly, you can overload. So plus, minus, division, multiplication. You can also overload the meaning of assignment operators like plus plus or equals or plus equals. We'll see that later this week. You can also overload the meaning of comparisons like equals equals or not equals or less than. We're going to see that later this week as well. And there's a bunch of strange operators that we can define our own meanings for. One example is this one. This is actually a bitwise operator that operates on binary values in C, but you've been using it all semester in C++ to generate output. That's actually just the result of operator overloading. We'll see an example of using this later this week as well. So now I have this ability to implement a perfect abstraction. I could make my type matrix not only as a type that represents the abstraction of a matrix and is encapsulated, but actually looks like a matrix when I use it. I can add them together, I can multiply them, which means I can now write C++ that looks a lot like linear algebra. And I think that's a big deal, and that goes a long way towards achieving this goal of the ultimate abstraction that we've been going towards.